All right, we're going to learn about making ethers. There are a couple ways to make ethers. Specifically, in this video, we're going to talk about using an SN2 reaction, and this process is more specifically referred to as a Williamson ether synthesis. That will impress your friends on Facebook or Instagram if you use that terminology. Okay, so for this reaction, we're going to do an SN2 reaction. So we know that we need a good nucleophile to do this reaction. And of course, for an SN2 reaction, we also need an alkyl halide. So let's see a nice simple example of this. Let's use, here's an alkyl halide. Note that I've chosen a primary halide. That's important. You can't do this on secondary halides, just primary halides. And we're going to treat this with a strong nucleophile. Our nucleophile is going to be an alkoxide. Because we're using an alkoxide, that's why we need to use a primary halide. If we use a secondary halide, the alkoxide might be inclined to act as a base and do an elimination instead. So primary halide ensures that we get our desired reaction, our SN2, and there we go. We made an ether. Fantastic. This is a great reaction. Works extremely well. Now, if you want to get a little bit more exotic about it, maybe in the first step we need to make our alkoxide. And we know how to do this. We can treat an alcohol with sodium metal. This will be our first step. This will make our alkoxide. And then step 2, we'll treat with our halide. You know, I've chosen bromide. You could use a chloride as well. And we'll do our SN2. This is properly the Williamson ether synthesis. And we get our product. Fantastic. Now, so in theory, when you look at just about any ether, you might be able to imagine putting it together with a Williamson ether synthesis. But we have to be careful. Here is an ether. And so when we make this by a Williamson ether synthesis, we could say, okay, I could make that CO bond, or I could make that CO bond. Let's label that A and B. Let's look at these. How would these work? If we wanted to make A, then we need the oxygen to be a nucleophile, and this carbon on the left is going to be our electrophile. So we might try to draw this. The oxygen is a nucleophile, attacks the halide, and kicks out the chloride. And that would make our product. Or we could try approach B. So let's make that A. Here's B. For approach B, we're going to use the same oxygen as a nucleophile, but we're going to attack that carbon instead. And that's going to make the same product. So which do we prefer, A or B? Well, the answer is we prefer B. B is the better approach because we are using, in this top case, we're using a secondary halide to attack. And when we use an alkoxide with a secondary halide, we're likely going to get an E2 reaction. An E2 reaction is a product. Here, since we have a methyl halide, we really are only going to get the SN2. So be careful how you take apart your ethers and you imagine putting them back together, because there's probably one way that's going to work better than the other. So be mindful of your substitution of your halide when you imagine doing a Williamson ether synthesis.